I think we're all here. Welcome back, folks. So I checked a couple of you are working on homework. For those of you who've started it, any questions? Not yet? You have a question? Okay, hit me.
No one's surprised. I shouldn't have had to start with. So it keeps saying, keep it in the model.
Mm-hmm.
That I don't understand.
That means rather than starting over and just putting in the new predictors, keep the ones you already had and add to them.
So in variable, I will add one before the slash.
Yes.
Okay.
Yes, that's what that means. So yeah, technically what you're doing is something called a stepwise regression, where you're adding variables in steps. There are various ways that you can let the computer decide what the optimal combination is. Forward selection, backward selection. I'm deliberately not teaching you that because it's not the computer's job to form and test your hypotheses. That's just not what we do in social science. So, but yeah, stepwise is sort of the name for what you're doing. So keep everything and then add to it at each step.
Okay.
Yep. Okay. Other questions? Is that your only one so far? Okay. Anyone else? No? Okay. Well, then that is due next Friday, so you still have a ways to go on that. I think I have stuff up for next week. Should I finish that? Yep. I have, we're going to finish this hopefully on Tuesday, maybe start some new stuff on Thursday, so I should have example 8 done either later today or tomorrow. So I'll let you know when that is ready. But for now, we get to start one of my favoriteest topics. No, for real. Because moderation is a thing, as I told you last time. There are whole books and workshops and programs written for this, and it is actually really easy. It reminds me of The Wizard of Oz. Do you remember the end of The Wizard of Oz, that movie? Surely you've seen The Wizard of Oz. Yeah, that's not like an age thing. Like, that's required of all people. But at the end, you know, there's like, pay no attention to the man behind the curtain. He has like this big voice or whatever, and it's a letdown because it's just like some random dude standing there. That's what moderation is like. It's like a big letdown once you realize it's really pretty straightforward. But so long as no one else knows that, it's yet another thing you can write on your list of skills that you have. You can do moderation analysis starting today. So once we start hitting models that examine moderation, that's where it becomes more challenging to explain what the model parameters mean in just words. It's helpful to have pictures. So I want to make sure that you guys know how to make pictures. In order to make pictures of your findings, you have to be able to create predicted outcomes to put in your pictures. So that's where I wanted to start today, is to discuss 3 different ways of doing that, in order of most annoying to least annoying, and to give you some options for doing that. So that's where we are here. This is lecture 7, slide 2. So getting predicted outcomes, getting y-hat values. That way you can actually plot like the slope of your variables. Like I've been making these plots all along, and I've given you some code, but I haven't really focused on it. So I wanted to go back over that and make sure that that was relatively more clear. So 3 ways to get them. Excel. That's one way to do it. You enter your coefficients. You enter values for your predictors that represent sort of typical or example values that you want to put your line through. You ask Excel, you write an equation to generate the predicted values, and you make a plot. So I often start here because it's good for pedagogical purposes to see how it actually works. The problem is that every time you have to enter something, you have a chance of screwing it up, right? Like human error. Plus, if you change your model, then the coefficients change and you have to change those, and so it's a tedious process. But it's good to start with. The second is via programming statements. So you actually already know how to do this. It's the idea of writing estimates or lincoms to create predicted outcomes, such as for the one group, the alternative group, when you have dummy codes. You can do it more generally, including any combination of predictor values, and get predicted outcomes. In SAS and SPSS, you end up having to write 1 line of code per value that you want to predict, which is not terribly hard, but it is time consuming. Stata has a thing called margins. that totally wins on this. This is one of my favorite things in Stata. It allows you to ask for multiple predictions in a algorithmic sort of way, and I'll show you what that looks like. And the third is something that I don't think I invented, but I'm pretty sure I'm the only one who calls it this. It's the method of fake people. You literally add cases to your data set that you're analyzing that have the values of the predictor that you want to generate predicted outcomes for. You do not give those fake people outcomes, though. So what ends up happening is that because they don't have outcomes, they don't contribute to the model. But every piece of software has an option that allows you to save predicted outcomes to a data set. And you can invoke that option to not have to write anything extra. It will create a predicted outcome for every case in your data set, including the fake people. Then you just subset to those cases and you make your picture. So there's 3 options for you, and I wanted to show you what each of those looks like, given the model that we just finished in the last example. So this is option 1, what it would look like in Excel. So we had a model that was predicting cognition. It had a fixed intercept beta 0, a fixed slope for age, a fixed slope for grip strength, the difference between men and women as a slope, the difference between none and future dementia as a slope, the difference between none and current dementia as a slope. So how many total fixed effects do I have in my model? 6, 1 intercept and 5 slopes. Good. So that means that every single one of these numbers has to go into my predicted outcome. Every single thing that's in the model contributes to what y hat is going to be, my predicted outcome. By the way, these are synonyms. Y hat, predicted outcome, expected outcome. Can you think of any others that you've heard of? I would add intercepts too, because intercepts are conditional outcomes as well. So that's the idea. Then, if I wanted to show, say, the effects of age and grip strength, that's what I have here. I generate people, fake people, so to speak, who have prototypical values that I want to use to show a range of my predictor. Now, what those values should be is based on your centering strategy. So they're centered versions, which is why you see negative and positive numbers here, because they're around the centering point. And the values should show sort of relatively low and high. What relative is depends on your data set. So in our data set, I chose -5 and +5 to show what it would look like for an 80-year-old, 85 is my reference, and a 90-year-old, because that's roughly plus or minus 1 standard deviation. 1 standard deviation was about 3 in grip strength, so I did the same thing. So I have 6, 9, and 12 as sort of my prototypical values. And I wrote enough lines to show every combination. So because I have 3 values of age, 3 values of grip, that's 9 total predicted outcomes that it takes to fill out every possible combination. In this plot, I'm not interested in the effects of gender or dementia, so I held them constant at 0. Later on, we will look at these effects more specifically, in which case these will get values instead. But for now, these lines that I'm going to end up with over here are for men without dementia. If they were for any other combination, they would be higher or lower on the y-axis accordingly, but the slopes stay the same. Okay, with me so far? So you would have to enter the coefficients from your model, enter values of the predictors for which you want to generate predicted outcomes, and then generate the predicted outcomes. So let me get out the actual Excel sheet that I used to do this that goes with example 7. And remember, this is the most annoying option of the 3, but it's good for pedagogy. So step 1, enter the coefficients. Step 2, enter the values. Step 3, generate the predicted outcomes. Okay. Well, you know what? You don't have to. But this is the easiest way to do math. That way you don't have to type a bunch of numbers in a calculator. It's functionally a calculator where you can do multiple calculations at the same time. But where I got this, you can see this. I'll double click. Unfortunately, there's no way to zoom in on the top. But in Excel, if you want to hold a reference to a particular cell, as you move a formula around, you put dollar signs for it. So this right here, $C, $3, means grab this right here and hold on to it. That's my intercept. So to generate a predicted outcome from my model equation, it's intercept plus slope times variable plus slope times variable plus slope times variable. So it's beta 0 plus beta 1 times the fixed effective age plus beta 2 times beta 2 is the fixed effects of grip. So for each of these, then if I'm going age, I need to multiply it by the value for age that goes with this. The coefficient for grip gets multiplied by the value of grip. The coefficient for gender gets multiplied by the value of gender, and so on. So the coefficients are over here on the left. The values are on the right. And by tying the coefficients to the formula, via the dollar signs, watch what happens. I can take my equation and drag it down like that. And then the one at the bottom still uses these exact same cells that I tied it to, but it interpolates or extrapolates. I'm not sure what the right word is here. It figures out that I want it to use these ones instead. Can we take a vote? Interpolate, extrapolate, something?
Extrapolate.
Extrapolate? Okay, we'll do that one then. So then it's using those. Yeah, isn't it? So yes. So why this is tedious and error prone, of course, you have to enter these things. And every time you change your model, these numbers change a little bit. You got to remember to change them. You got to make sure your formula is correct and ties the exact right things with these stuff. And then once you get to this point, what you have is a set of 9 values. They're organized by age and grip, but Excel doesn't intuitively know that. So I have to take these values and transpose them into a format that I can use to make a picture. So I took this for this one, for the second one, come on, for the third one, and so on. And then you can make your picture. So that is the file that goes with the example for this, by which I generated this. So what this shows then is the effective grip strength, because grip is on the x-axis, for different aged people. And the fact that each of those variables has its own independent effect in the model, known as a main effect, unconditional, results in predicted outcomes that form parallel lines. So the effective grip is the same no matter what age you are. Likewise, the distance between these lines that indicates the effective age is the same no matter what grip you are. Age and grip operate additively, in other words. Question?
Clarifying question. So what we've created, is this hypothetical or is this like real?
We have generated predicted outcomes for hypothetical people that are motivated by the real ones.
Okay.
So there may not be anyone in the data set that is exactly age 80 with a grip strength of 6, but it's plausible based on the distributions of these variables that there could be that kind of person. So I just picked low, medium, high, basically for each of these, and I did every combination. So there's no values of these that are right or wrong. It's just sort of, you want to show something that looks plausible to demonstrate what low and high would look like. Okay, with me so far? So has anyone made you do anything like this before in your lives? Not really? Yeah, that's because this is a pain in the ass. But it does demonstrate that you know how to make a predictive equation. So, if you're willing to let the computer do it for you, here's option 2. Writing estimate statements that build the predicted outcome. So here's what it looks like in SAS. The next page has it in Stata because it's going to look different. So I have 9 estimate statements here, and every single one of them has every variable that's in the model. The coefficients that go after it fill in the values for that variable for which I want the prediction. So intercept, I need one of those. Essentially, the variable that multiplies intercept is a column of ones. If you do a matrix version of the model, that's what shows up here to make so that intercept gets added to everybody. Then I fill in -5, and then 0 and 5 for my age, -3, 0, 3 for my grip. I zero these guys out. So what's implicit here are the plus signs. Anywhere that there's a negative sign, it's a minus sign instead. But these are the estimates that we get, and if you were to check these against Excel, you'd see that they are exactly right. The benefit of doing it here, though, is that Excel only gave me that first column, right? It gave me the predicted outcome. It did not give me standard error. It did not give me any of this other information. So it is common when people make plots of these sorts of lines to put error bars around them to convey the uncertainty of each prediction. Plus or minus 1 standard error or 2 standard errors sometimes. It differs by field what the convention is. But doing it in a program allows you to get those standard errors very easily by which to make those bars around your prediction. So that's very helpful. Once I have this piece of output right here, I have to save it as a data set to be able to add more columns to indicate the values of age and grip that are contained in these labels. So that's this part right here. So I have a little data step where I'm using a character function. So the function index searches through this column of words. If it finds the word in parentheses that it's searching for, given next, it tells me where it is. So in other words, what this is doing is, if the string has this in it, then it's age 80. If the string has that in it, it's age 85. And so I coded age and grip as variables so that I can then use those, grip as the x-axis in a plot statement, and age as the grouping variable. And this is the lovely little plot that SAS made me. Now it's sort of weird to have the lines in the middle, but I wanted to be able to show that you have options in what your x-axis and what your y-axis is. So this is why I have it going from 3 to 15, even though I only have values in the middle here. So that's not so bad. You have to set up the code, but once you have it, if you change your model, you just rerun the code and all the values update themselves. So that's not so bad. Plus, if you had, say, 10 different outcome variables that you were examining, all you would have to do was swap out what your outcome is, and then you could use this to make 10 plots. Real easy. Okay. With me so far? Okay, now, Stata people. Let me show of hands, people who have to pledge allegiance to Stata. Just this side of the room, apparently. You guys have, like, segregated yourselves. See, this might be enough to make you a Stata person. All of this is done by this one thing. Stata wins on this. I've never seen any other program that does this so nicely. This thing margins at, and then you list the range of values. So the way to interpret what these numbers mean is I wrote in here in a comment, start from -5, go in increments of 5 up to 5. Do the same thing for grip, starting at -3, in increments of 3, go up to 3. There, that gives me my 9 values right there. Sweet, huh? And then, margins plot. Can you take those values and make a picture? Thanks. And I'd like it to be the x-axis is grip, and there's the picture I got. So it pops up in a little window. You can double click on each aspect of it and label things and make it different colors or do whatever you want. And note that it gives the error bars on here by default. So if I were putting this in publication, I would probably change a few things. Like the x-axis, having it go from -3 to 3 is weird. Like you'd want to show the actual values of grip, not the centered values. Linear predictor is a terrible name for your y-axis. What they mean is predicted outcome from your linear model, from the fixed effects. So like predicted cognition would be a much better name. They have done what I refer to as cheating the y-axis. So cognition does not go from 24 to 34. They pick these values to make your plot look as impressive as possible. You would want to plot the y-axis on a range of at least probably plus or minus 2 standard deviations. That way it doesn't look like you're cheating to make your effects look dramatic. Same thing here, like the legend. This is a bad legend. I would go with, age equals 80 as opposed to age 85 equals minus 5, which is a mental gymnastics that your reader does not want to have to engage in. Right? Yeah.
I don't understand, but I wonder why in the post it says it's 5 instead of 0.
This right here.
Yes, on the screen.
So it's going from minus 5 to 5, and the middle one in parentheses is the increment. So it's going to go minus 5, 0, 5 because it's going in increments of 5. Like if I wanted minus 5, minus 4, minus 3, minus 2, I'd say in increments of 1. Yep, so it's very flexible. And I'm sure there are ways to write code to change all of these things. I was just too lazy to learn them because I don't use Stata for very much. So, but know that it's out there. So the core idea is just to be able to show what does your model say and to make a picture of it. So if you're giving a presentation or if you're giving a poster, I tell you what, if I ever come to a talk of yours at a conference and you have a slide like this, I will hunt you down and slap you because this is incorrect. No, you do not give posters or talks with tables of numbers to a professional audience, right? What you would talk about, or coefficients, right? This also was thwapful. Thwap is my because no, people don't want to see tables of coefficients. What you would do is put up a picture like this and be like, as you can see, grip strength had a positive effect, and the difference between the lines shows the effect of age, which was negative, right? That's how you would do it. So being able to generate these sorts of pictures is very important for communicating your results to regular people and to people quickly. So, question or itching?
Sorry.
Okay. Yeah, I've already had my allotment of caffeine today, as you might be able to tell. So I'm just going to take a sip. Invite questions from the audience. Yeah, my slides are very different when I give talks than when I teach. Yeah.
What if we have 2 or 4 variables?
2 or what? I'm sorry?
What if we have 4 variables?
More variables?
Yes.
So this only shows the effect of 2 of the 5 variables in my model. If you wanted to show the others, you could choose to hold age and grip constant and then make a plot for men versus women, maybe another plot for the dementia types. So long as the variables only have additive effects, which is true right now because each of these variables only has an effect all by itself, you're not really missing any story by holding some of the variables constant and just showing others. Now that changes starting today when these things are going to have not just additive effects but interactive effects. But yeah, have as many pictures as it takes to show the story, to answer the questions. Okay. All right, other questions? Okay. So just to recap, you can generate predicted outcomes in Excel. That's good to demonstrate that you know what the computer is actually doing. Bad in the sense that it's error prone and doesn't give you standard errors. You can write programming statements to give you the predicted values. Good in the sense that you know what it's doing. Bad in the sense that it generates a lot of different statements. Or way number 3, fake people. So this is what I do when I have a lot more complex analyses to do where I don't want to have to keep track of all the things that would change if I change the model, because this works for any combination of models so long as you're using the same variables. So let's say that my goal was to make that same plot of age and grip strength effects. I'm starting off with something you haven't seen yet. So by the way, Stata people, you can like take a nap for a few minutes because you don't have to do this because you have margins. This is for programs that don't have margins like SPSS and SAS. I'm making a new data set called fake people. Input is the list of columns it's going to have. Before I put in the data, I also repeat the code to create the centered versions of the predictors so that they'll have those there. And then data lines, this is literally me hand entering the values that go with these columns. So person ID, I am setting to -99. Do you know why I chose -99? Because when people have ID variables, they rarely include negative numbers, number one. So that's a good giveaway that this is not a real person. And second, if I were to sort the data set by ID number, they show up first. That way I can easily go in and grab those values and not have to scroll and scroll and scroll. From there, I'm doing the same thing that I did in Excel or in writing those statements. I've got 3 values of age 80, 85, 90, the values of grip, and I'm doing it in the metric of the original variables. It's going to create the centered versions and append them for me, and I filled out zeros for everybody else. Then I take this fake data set and I merge it with my original one. So because these fake people don't have outcomes, they're not going to be included in generating the model parameters. They are not going to hurt anything. I'm not cheating. The model won't use them. But what is going to happen when I run this same model is that it's going to create a data set of all my people that the model was run on, including the fake ones, and add a column for the predicted value that's y hat, that I've named it, and the standard error for y hat. And then that data set has the predicted values, and all I have to do is plot them. And so this step then is me running the model, and then the code to plot it is just literally this again. So this is the easiest of the 3, I think. You generate fake people that have the values you want to plot, you run your model, you run your plot. Okay. Does that make sense? Maybe? Maybe. It's one of those things you could practice, but it's good to know how to make pictures. Pictures are going to be very important. All right. Now the new stuff. So when are pictures especially important? When you have interaction terms. And I can see it. Pictures are important, but they're really important once you have interactions. Let me move this over. Somehow it got to... So an interaction term looks like this. So here's an example. General linear model. We're still sticking with that same family. Where you know what beta 0 is, right? What's beta 0? Intercept, which is the... Well, we don't know what the variables are yet, but we know that it's the expected outcome when what is true. The predictors are 0, so when x is 0 and when z is 0. Beta 1 and beta 2 should look familiar, right? Those are going to be your fixed slopes. So beta 1, you would say that that's the change in y per unit change in x. Beta 2 is the change in y per unit change in z. And you know what E is, right? What's E? Residual, or E stands for error. Sometimes E is a little r in other people's notation, stands for residual. And E represents how far off your real outcome is from the one that is predicted for you using the betas. So it's the idea that the model has a residual variance. A variance of the E's to be estimated to describe how much more information there is in Y that we don't know why it's there yet. Now the new thing. X times Z as another variable. It's called an interaction. Beta 3 is the slope of the interaction. So what that interaction term is conveying is that the effect of x depends on what z is. Likewise, The effect of z depends on what x is. There's a conditionality. Is x always better? Well, maybe once you get to a certain point on z, x doesn't help you anymore. Or maybe the effect of z is stronger in certain x people than others. It's the idea that you can't just say, yes, there's an effect of x. Well, it depends. Sometimes there is, sometimes there's not. There's a conditionality there. One of these things, when you talk about what the interaction term does, is usually labeled as the predictor, and the other one is labeled as the moderator. That is a set of words that has nothing to do with the math. So remember how like a control variable is a predictor that someone else cares about? Like a moderator is a thing that it's like, oh, I want to know if this is what it depends on. And someone else might come around and say, no, the x is the moderator, not z, whatever. They're both in there. Now, this is a topic that I always have to start with in my advanced classes because there is such heterogeneity in how people are taught about it. And it boils down to the same sort of silos by which the general linear model has been taught, historically, including to myself. So we can always examine interactions like this. We can do it for any kind of predictor variable, and we can do it for any kind of outcome. If we're working with quantitative outcomes, we're in the general linear model world, but we can have interactions of binary predictors, nominal predictors, quantitative predictors, anything. However, so analysis of variance, right? What combination is called analysis of variance? What kind of predictors? Categorical, right? So if you were to say generate an ANOVA in SPSS, do you know what it does by default when you have more than one categorical predictor? It estimates every possible interaction among them by default. And people are cool with that. You get this enormous set of output, like if you have an experimental design, right, where you've manipulated one factor and you have two levels of it, and you manipulate another factor and say there's two levels of it, and you manipulate another factor and there's two levels of it, you would say that you have like a 2 by 2 by 2. And so you end up with, if you estimate everything you possibly could, a 3-way interaction, 3 two-way interactions, and 3 main effects. And you ask SPSS for this, and it goes and gives it all to you. And there's usually no attempt to trim the model to get rid of things that are non-significant, to simplify it. You just sort of go in and be like, that one has a p-value I like, and that one, and this one over here. And that's it. If you do ANCOVA, remember what ANCOVA is? It's ANOVA with what else? What's the co part?
Covariance.
Covariance, things someone else cares about, meaning that they are quantitative predictors. A traditional ANCOVA model has something called homogeneity of regression. What that means is that it assumes that the covariates only have additive main effects. They do not participate in interaction terms. Now, there is no reason why they can't, but then it's just not called ANCOVA anymore if you put that in. Likewise, regression. Traditional regression involves only quantitative predictors, and there is no default interaction terms. You have to decide which ones you'd want to have as interactions, and usually create them manually as another variable in your data set. The syntax that I've showed you doesn't require this, but a lot of older school programs do. So depending on like what class you're taking, even though it's the same general linear model, you may go from no default interactions to being told you can't have them to being told that you have to have every possible one. So the perspective that I have and that I've written about in Chapter 2 is that it's up to you to figure out what interaction terms are necessary to answer your questions and in order to believe the results of your models. So testing interaction terms probably should happen even if you don't have a reason to expect them, because if they're there, you got to know about that in order to interpret everything else correctly. So there's no like you have to do everything and you have to keep everything. I would keep what is necessary in terms of the model results, what is significant. And if things are not significant, you may have to keep that in order to answer your question. So if your hypothesis is that the effect of x is varying as a function of z, and that's not true, you got to keep this interaction in the model to say, I was wrong. Here's evidence that I was wrong. I'm going to retain the null hypothesis that there is no interaction. So we're going to learn how to do interactions of every kind. Cool? You're looking not cool. Cool? It's cool. Moderation. Danae asked me a question, are we going to do mediation? Do you know, have you heard this phrase before? Mediation? Mediation and moderation get shoved together a lot, but they are not the same thing. So mediation, I'll just do this real quick because you've actually already learned how to do mediation, you just didn't know it, because it's another thing that has marketing. So mediation is always shown with a picture that looks like this. Not a model, but a picture. The idea of mediation is that your X predictor causes some change in M, and it is the change in M that is responsible for Y. It is a mediator, exactly. So cause is the word here. So it's typically used in intervention sorts of research where X is a manipulated variable, and they track X's effect on something else that's not manipulated, and whether or not the effect of Y is still, whether or not Y is still predicted by X after controlling for M is demonstration of mediation. So it's whether or not this relationship still needs to be there. That's mediation. Now the reason I say that you've already learned this, let me phrase this again. If I have a model in which I put X in the model and it predicts Y, how do I know if X still predicts Y after controlling for M? We just did that. You put M in and you see if X still has an effect. The end. That's mediation. But no, mediation has like extra words and symbols and stuff that goes with it. There's a marketing campaign around it that's unbelievable. But that's what regression does. It allows you to say, is blah blah still significant after controlling for blah blah? There's just, this picture that goes with it. And also people are interested in estimating the effect of that path multiplied by that path. It's called an indirect effect. In order to do that directly, we can't do that in regression, because in regression, M can either be a predictor or an outcome, but not both, whereas this model needs it to be an outcome of X at the same time it's a predictor of Y. But the big difference is that mediation is supposed to be causal. Moderation just means that the effect of a predictor depends on another predictor. So if I said the effect of golf training depends on your previous experience, right? That's moderation. In order for previous experience to be a mediator, I would have to say random assignment to golf training categories caused your previous experience, which then causes your outcome. Exactly, that look, no. There are a lot of people who mistakenly use the word mediation when they mean moderation. If the variable in question cannot logically be an outcome, it can't be a mediator. Things like age. Can age be a mediator? Can you think of anything that causes age?
Time.
Yeah, being born, and then after that, like the calendar, like the end, right? That's your causal mechanism of age. So things like age, gender, any characteristic that can't be caused by something, those can be moderators, not mediators. So they often get confused because they're taught at the same time. If you come back next semester, I will teach you how to do something called path modeling, which is literally this, where you can do all of these relationships at the same time. And I'll teach you the fancy mediation words so that you can add that to your list of skills as well. Okay. Question?
Something I read just I know I have it.
Sure.
So the outcome at the same time be a predictor of y?
Yes.
And that is a moderator.
This is a mediator.
That's
This
a
is the mediator.
Okay.
Yeah. So the reason that we can't do this model simultaneously in regression is because M has to be an outcome of X at the same time it is a predictor of Y. So there are sort of old school approaches where you do this in steps. Like you run one regression model where M is the outcome of X. You run another regression model where Y is the outcome of X. Another regression model where Y is the outcome of M. Like, bleh. I mean, that's how you can sort of work your way into it. But that approach becomes intractable once you have more than one outcome and more than one mediator at a time. So I'll teach you how to do it simultaneously. It's just regression with a bunch of outcomes at the same time, but that's next semester. We're doing moderation today. Okay, so moderation, we're going to do it. So, little new vocabulary. I introduced this to you last time, the idea of a main effect. The slope of a variable by itself, you can refer to as its main effect. When there are no interactions in your model, you can think of your main effects as marginal, meaning like the effect of X applies to all levels of grip strength. The effect of age applies to all levels of grip strength. Like that's the idea of the parallel lines, that the effect of one variable has nothing to do with the effects of the others. That is not true anymore once we have interaction terms, and so we have to change the language we use to describe the slopes as well as what they mean. So if you have an interaction in the model like X and Z, rule number one, the main effect of X, meaning beta 1, and the main effect of Z, meaning beta 2, stay in the model. So if you're looking to simplify your model by getting rid of slopes that have non-significant effects, you cannot get rid of the variables' slopes that are by themselves when those variables are part of an interaction. You cannot. Otherwise, the interaction does not mean what you think it does. So that's rule number one. What the interaction does is adjust its main effect slopes. So the main effects change their interpretation accordingly. They become conditional on when the variable that they interact with is 0 specifically. So if we look at this example model right here, I have beta 1 as a main effect of X, beta 2 as a main effect of Z, beta 3 as a main effect of W. So those are still slopes, but I'm using a special term, main effect, because it's referring to a single variable by itself. Now note, W does not show up in any other term. So beta 3, the main effect of W, is unconditional, is marginal. This is the slope for W no matter what. No matter what your X is, no matter what your Z is, everybody gets the same W slope. That's what has happened up to this point. And that's what would still be true for W in this model because W isn't involved in any other terms. Not true for X and Z. Each of those main effects become either, you can call them simple main effects or you can call them conditional main effects because they are the main effect of X specifically when the predictors that they interact with are 0. In this case, the slope of X is specific to people who have a Z of 0. The slope of Z, beta 2, is specific to people who have an X of 0. That's their new definition. So the conditional is the when something else holds. So this is a different kind of thing than holding constant. So previously we talked about the effects of each of these predictors is holding constant the other predictors. Remember that language, like after controlling for? This is not only after controlling for, but constant at a particular value of the interacting predictor. It's an extra level of conditionality. Because the only time when beta 1 would be the only term that relates to X is if Z is 0, in which case that goes away. Then beta 1 is the only thing that tells us what the slope for x is. Likewise, the only time that the effect of z, the slope of z, is governed only by beta 2 is when x is 0 and this drops. So that's what they mean. They are specific to when the interacting predictor equals 0. Now what to do with this thing, the interaction term? This is what people don't get taught. But you actually know already how to do this. Do you know what interactions do? They take their main effects and they do one of 4 things. More positive, less positive, more negative, less negative. That's it. That is the sum total of all possible moderation. All you got to do is figure out which of the 4 you're in. So let's practice. So let's say that I have this model. I'm dropping out W to simplify things. So we have an effect of X, an effect of Z, and their interaction. So if I focus on this first line here, let's say that beta 1 has a value of 10 for the slope of X when Z is 0. Beta 2 has a value of 5 for the slope of Z when X is 0. And beta 3 has a value of 2. So to complete the question mark portion here, fill in the blank. Beta 3 makes the x slope, so I know the x slope is positive, right? That means it's either going to be more positive or less positive. I know the interaction is positive, so this is more positive. Beta 3 makes the slope for x, beta 1 itself, more positive by 2 per unit z. So note y is not in this page. What happens is that beta 3 changes beta 1 then changes y. So it's like trickle-down economics or something. Yes, thank you. Fellow person who remembers Reagan. How'd that work out for us? I forget that part. But. Likewise, if I want to focus on what beta 3, the interaction term, does to the slope of z, same story. Beta 3 makes this z slope of 5 more positive by 2 for every unit x. So we focus on one of the slopes and talk about it as a function of what happens to the other predictor. The other predictor is deemed, that's where we want, the moderator. I was going to go with deemed and termed, and it turned into teamed. Okay. Now this one, because it's still 10 and 2, this is positive, right? But this one's different. If I talk about what happens to the slope of z, z is minus 5. My interaction term is positive. So as x increases, my slope of z does what? Two counteracts my minus 5. This is a less positive. As x increases, the slope of z becomes less positive by 2 per unit x. So at x is 0, beta 2 is minus 5. If x goes to 1, then the slope is minus 3. If x goes to 2, it goes to minus 1. So it becomes less positive in this case. So when a slope is heading towards 0, when it is less positive, such in this case, it's becoming weaker. When a slope is headed away from 0, such as more positive, it's becoming stronger. How about this one? If I have the slope of x is minus 10, what does the interaction term do to it as z increases? So the slope I'm starting with is the slope of x is minus 10. As z increases, what does this interaction of 2 do to it? It moves, in this case, it's going to move towards 0 because we're going negative 10. It's going to get less negative by 2. So this is another less negative. This is another more positive by the combination. These are both less negative. Now this one. If I have a slope of positive 10 for x and an interaction with z of negative 2, what does my interaction do to the slope of x as z increases? These two numbers, less positive. It was 10, but the interaction term is negative, so it's going to bring it down as the interacting variable increases. So this is a less positive, and this one is the same. So if my slope for x is 10 when z is 0, when z goes to 1, what will it be? So the slope of x is 10 if z is 0. The interaction term makes it less positive by 2 per unit increase in z. So if z increases by 1, what's the net result of these two? It's 8. So the new slope, if z were 1, would be 8, less positive by 2. And if z were 2, it goes down to 6. And if z were 3, other way.
Sorry. Sorry.
4 down to 4. So once you figure out which you're in, that's it. Now, functionally speaking, less anything means weaker, more anything means stronger. So that's where you can start getting out your GRE vocabulary to replace more positive, less positive, more negative, or less negative. So you can say for more positive that the effect is magnified at higher levels of the other variable. It is enhanced. You think of other ones? What stronger effect? The other way, if I want to say something is something less negative, it is diminished, it is reduced. This is where we start getting to things like protective factors. Yeah, doesn't that sound familiar? Like if something has a negative effect and the interacting variable reduces that negative effect, it is a protective factor. But there's a difference between a negative effect getting less negative and a positive effect getting less positive. Right? It depends on whether or not what happens initially. So if I said that the growth rate for something was less positive as a function of some other variable, they're still going up. They're going up less. So the initial positive versus negative matters in talking about what's happening. Is something becoming weaker or something becoming stronger? So this one is another less positive. Now what's this one? We haven't done these two yet. If I have a negative slope of z and a negative interaction with x, what happens to the slope of z as x increases? More negative. It makes stronger. How about risk factor? How about that? Yeah. So you get the idea. We'll do lots and lots of practice with this. Yeah.
Here's a question for one. On the last column from the second row on the top, how is that, the second row on the top, on the white, how is that interaction less positive?
Oh, this is a less negative. Thank you. Thank you. Yeah, now I'm checking the rest of these. Less negative, more positive. Less negative, less negative, less positive, less positive. Less positive, more negative. What's this one? That's a more negative. And this one? Less positive. And last but not least, these are both more negatives. Yep. So yeah, I didn't really need so many entries, but I wanted to practice. Save. All right. So this is the point, by the way, where in typical regression classes, people would start saying, oh, you need to center your variables. We've been doing that the whole time. But I'll show you why it really matters in the context of these interactions. Say, I'm not out of time yet, am I? Okay, good. Okay, so let's say we have a story. I'm predicting GPA as a percentage grade out of 100 from an X variable that is parent attitudes about the importance of education measured on a 1 to 5 scale, and Z is a father's level of education measured in years of education. Let's say that I have this model right here that hypothesizes an interactive effect of attitudes in education. I put the variables in directly as they are in my data set, no centering, and I end up with this regression solution for my fixed effects. So let's figure out what each one means. So the intercept is 30. 30 is, what's an intercept again? Expected Y, which is GPA in my story, when predictors are 0. So when is attitudes 0? On a 1 to 5 scale. They really don't care. They're like, oh, I'm not even going to answer this question. Give me a 0. And they never went to school. No wonder they don't care. So that would explain why the GPA is predicted to be so low. Now, do you think there's anybody in the data set that's like this? I know it's just a fake story, but do you think they'd fill out a questionnaire? Right? Like, let's be real about selection bias here. Okay, so the intercept doesn't mean anything, but we don't need it very much anyway. So let's do the next one. Beta 1.
So for that, you still run it, right? Like you have to still run it, even though it like makes no sense.
It has to stay there because what it does is adjust Y for the difference in means of the X predictors. And it serves as your model reference point too. So when you talk about an increase in X, like it's relative to the intercept is what you're talking about. So the slope is always the change in Y per 1 unit change in X. So we'll go change in GPA per unit attitude. Now am I done or do I have to keep typing? I'm not done yet. There's conditionality. When is beta 1 the only thing that contributes to the slope for attitudes? When education is 0. When ed equals 0. Do you think we have anybody in the data set that has education of 0? No. So that coefficient of 1 probably doesn't help us very much. Next. Change in GPA per unit ed when attitudes is 0, which can't even happen. So we are 0 for 3 with coefficients that actually mean anything. Yeah, it's dissatisfying, isn't it? I think so. Now let's do beta 3. The pattern here is all positive numbers. So which of the 4 are we in, no matter which predictor we look at?
More positive.
These are all more positives. Beta 3 is going to take the slope beta 1 and make it more positive as a function of education. It's going to take the slope of education and make it more positive by attitudes. So if we start with attitude as the moderator, then what we're saying is that, get the colors here, beta 2 becomes more pos by the interaction coefficient per unit, which one? Beta 2 is already for education. It's got to be the other one. It's per unit at. So beta 2 becomes more positive by beta 3 times at. If I go the other way, beta 1 is the slope of education, more positive by 0.5 per unit. Oh, wait a minute, I typed it. I did the wrong one. Attitude is moderate. No, that's right. Yeah, per. This one's got to be ed. This may be an instance in which once I show you the algebra, you'll like it better. Because it makes it easier to see why these things work out the way that they do. But yeah, if we talk about attitude as the moderator, then we're focusing on interpreting the effect of education. The effect of education is 2 for somebody who has an attitude of 0. As attitude increases by 1, that 2 becomes more positive by 0.5. So if attitudes equals 1, it is 2.5. If attitudes equals 3, it becomes 3. Or attitudes equals 2, it becomes 3. There we go. Now the other way, if we focus on the slope of attitudes as the thing we care about and education as the moderator, then we're starting with beta 1 is 1. So the slope of beta 1 is for attitudes when education is 0. For every unit higher education, that slope of 1 becomes more positive by 0.5. So for somebody who went to 1 year of school, it's going to be 1.5. 2 years of school, 2, and so on. So the good news is that the model tells you what the slope is going to be for any value of the interacting predictors. There is a formula by which you can figure it out. The only ones that are given to you directly as model parameters are specific when the interacting variable is 0. And that's why it really starts to matter in terms of how useful your coefficients are, that your predictors have a meaningful 0 value. So before, up to this point, it just changed our intercept. But now if we don't center, it changes our main effects as well. And it makes them potentially useless. So that is to say, when you're running these models in practice, if you started with a model that only had attitudes and education as main effects, you'll get a set of coefficients for it. You'll get a slope for attitudes and you'll get a slope for education. But those are unconditional slopes. That model says the same slope holds for everybody for attitudes and the same slope holds for everybody for education. If you then add this interaction term and run a new model, beta 1 and beta 2 will change because they mean something different. They are now the slope of these variables specifically when the other one that it interacts with is 0. So they will change numerically because they mean different things. That means they have to stay as part of this package. So funny story to end on. APA, you know, the way we all have to write, they're coming out with a new version like this fall, so yay. Now I have to figure out if I have to italicize or underline or like all those, you know, stupid things. But one of the things that they do is publish a book that has like example tables and figures. And there's one for a set of regression models. That's wrong. Because they try to save space for a stepwise regression, meaning that you have a set of predictors, you add some more, that involves interaction terms by only giving the main effects from the main effects model and then only adding the interaction term and not repeating the main effects. In other words, they give you beta 1 and beta 2 from a model without this, and then for the next model, adding the interaction term, they leave them out, thinking they're redundant with what's already reported. Incorrect. They mean different things. And they will only be exactly the same across models if you center these predictors at their exact grand means. Then they will be the same. But they still mean something different. And their standard errors are still going to be different because they're conditional on a point, they're going to be bigger, and their significance levels may be different. So it is entirely possible that a predictor that looked like it were significant becomes non-significant once it's conditioned on when something else is 0. But do you get to kick it out? Nope, it stays. Because beta 3's job is to adjust beta 2 by the other variable and to adjust beta 1 by the other variable. They have to stay. Otherwise, you're assuming they're exactly 0, and that causes problems. So what if we fixed it? By centering. I've centered attitudes at 3, near the middle, education at 12, which may not be near the middle, but it's a nice convenient reference point. So I got my 75 from the previous model here by plugging in the values of the coefficients and the values of the predictors that I wanted to change to be my new centering points. So 75 is expected GPA when? What's my new intercept? Ed is 12, and add is 3. That seems pretty reasonable. Beta 1 is change in GPA per unit, change in at when Ed is, same rule, when the predictors are 0, but what's my new 0 point? 12. So now this is the effective education amongst people with high school degrees. Could happen. Likewise, change in GPA per unit, change in Ed when at is, what's my new 0? 3. So that's the difference per year of education for people with middle of the road attitudes. Now note, the interaction coefficient did not change. It will not change because it is the highest order term with respect to its contents. It is unconditional with respect to centering. So the beta 1 becomes more positive by 0.5 per unit Ed. Beta 2 becomes more positive by 0.5 per unit at. That's still true. The difference is the reference points for where the slopes are. They have changed to something that is more in the middle of the data, and thus which is more useful to us. So these new numbers right here, any guesses as to how I got those?
2.5 is the attitude with the 0.5.
Mm-hmm.
Right? Yes, okay.
Yep, they came from my previous model. Let me turn. Right? The interaction tells me. So if I move from education equals 0 to education equals 12, 12 times 0.5 is 6, right? And this is my starting point. So 6 plus 1 is 7. That's my new slope. Likewise, 2 is what it is when attitudes is 0. If I want attitudes to be 3, what's 3 times 0.5? 1.5 plus 2, 3.5. That's where they came from. The model tells me any simple effect, as it's known, simple slope, simple main effect of attitudes or education, not just the ones that are conditional on 0. But just doing the math like that doesn't get me their standard errors, and it doesn't get me their p-values. But can you guess how I can get them? Put it in the software. They're linear combinations. You already know how to do this. Estimates and lincoms. So I'll get to show you how that works next week. See? Isn't this cool? It's going to take a minute. Yes, it is. But once you see it, you can't unsee it. It's like the magic eye posters. The irony of that analogy is that I can't see the magic eye posters. I've never been able to. But I hear there's a sailboat. So there's a Mallrats reference for you. So. All right. Office hours later today. Let me know if you need help with your homework or otherwise. Have a great weekend.